Let's get a bit more formally into equations now to explain the low latitude atmosphere and ocean dynamics. This is not a fundamental text, it's an advanced book in that sense, so the equations are not derived from scratch, but I have the derivations including going from non-rotational framework to framework and going from a flat rotating surface to the sphere in terms of Coriolis effect, etc. in my ocean atmosphere dynamics course on my channel. But here we start right away with these full F equals ma equation and the continuity, energy, and equation of state. This obviously is a vector velocity UVW. Unit mass, you can think of density as F equals ma. So the forces include the pressure gradient forces in the vertical and horizontal. It's a negative sign because it depends on whether it's compressing or expanding in terms of which way the motion happens. Or you can think of a parcel of air. You have pressure on this side, pressure on this side, and then you subtract this and this, use Taylor column and all those beautiful things that I show in the other course. And you have the gravitational force in the vertical, and you have Coriolis effects. Plus some dissipation in the system. Continuity equation is written here as d rho dt plus rho grad dot v, non-flux form. In this book, the convention d dt corresponds to the full derivative with partial dt plus u d dx v d dy w d dz, which in a strict protocol has to be capital D because this D is sometimes used for a variable that's a function of only one one variable. So rho, if rho is only a function of time, then you would write it as d rho dt, but in this case it's actually partial rho partial t plus u d rho dx v d rho dy w d rho dz. This allows us, we will see soon, to make assumptions about nearly incompressible atmosphere, in which case we will ignore d rho dt and assume that the divergence term is equal to 0. Valid in many cases. The energy equation, of course, relates the heating to diabatic heating to the isentropic variability or isentropic potential temperature variability, and equation of state P equals rho RT, because dry air and moist air both behave like ideal gases. Just to orient ourselves, we have the longitudinal direction, we have the latitudinal direction with the radius of the Earth A. We are looking at height z above the surface or depth z into the ocean, and we need distance from the center of the Earth to z, which is r, which is obviously a plus z, and radius a, 6371 kilometers, is much larger than z, which is at best order 10 kilometers. So that allows us to make assumptions like 1 over r being just approximately equal to 1 over a, because a is much greater than z, which means partial with respect to r can be just written as partial with respect to z. And using these local Cartesian unit vectors I, j, and k, we can write the equations where u, the longitudinal velocity, becomes r times cosine phi, which is the local projection, times d lambda dt, which is the time rate of change in the longitudinal direction as you are moving east to west, and v is r d phi dt, latitudinal change in time of a parcel of air or water, and w is of course dr dt, motion in the vertical direction. Okay, so already you can see the advantages there. Coriolis, obviously it's the effect of rotation around Earth's axis. which is given as minus 2 omega cross u when you do the derivation. I'm not going to go into the details, but just wanted to point out how the local projection of Coriolis happens. So when you are again in this direction of r, the local z, you are going to translate that rotation of Earth to local. So this is the local rotational effect around the Earth's axis, and here is your local x, y, and z, and that's parallel to omega, and there is the latitude. So you want to see what is the projection of omega locally in the three directions, the longitudinal, latitudinal, and vertical directions. So you can split omega into the meridional direction, vertical direction, and the longitudinal direction. So omega cosine phi is parallel to meridional direction. It turns out, if you just remember that Coriolis pushes things to the right of the direction of motion in the northern hemisphere, then you can see that this component will produce a vertical Coriolis effect, which is in the same direction as gravity, and it turns out to be about 1,000 times smaller. So for all practical purposes, we just ignore the omega cosine phi part of the local Coriolis effect. We will see this in a little bit more detail later on. But the vertical component of omega locally produces to the right, so in the longitudinal or latitudinal direction, depending on which way you are moving. Right? Perpendicular to z means either in the meridional direction or in the longitudinal direction. So it is the local vertical component of omega, which is omega sine phi, that we retain. So then omega is, as a vector, is locally written as 0 in the x direction, omega cosine phi in the y direction, and omega sine phi in the z direction. Why is the x component 0? Because obviously omega is locally orthogonal to x and has no projection on x. Okay, so there is minus 2 omega u, and you will end up with minus 2 omega cosine phi u, which is in the direction of gravity, and we ignore it. Remember, u here is a vector, and this is minus 2 omega sine phi, which is the horizontal component of the Coriolis effect. So omega cross u in that sense is written as 0 omega cosine phi omega sine phi cross with UVW. So you're going to end it these three components, and with hydrostatic assumption we will see what happens to this. This is 0 because it's in the vertical or gravitational direction, much smaller than gravity, and this is in the meridional direction. Okay, so let's look at d dt then, the total derivative partial t in the lambda phi r plus v dot grad with t constant equals d dt lambda phi z, because r is a plus z, which is a is much greater than z, so we can just replace it d dr with d dz as we saw before, and u or cosine phi partial lambda in t phi z held constant, v or a, so this is zonal meridional d d phi tyz plus omega d dz and so on. So here vector v is r cosine phi d lambda dt I plus r d phi dt j and dr dt k, because r is only a function in the z direction. We can write it as u plus v plus w I j k. So it's a mix of non-Cartesian coordinates, so not just x, y, z. You have geometric terms, as we will see, relating to cosine phi and sine phi and so on. So we have to carry these terms when we look at the equations further. Let me come to that in the next podcast. So we started with the equations of motion and started to look at what it means when we are on a sphere and in a rotating framework.